Third time's a charm. So, good morning, everyone. This is Tony Mason. I'm lecturer for CPSC 416 this term. Today is March 14th, 2023, and I have a guest lecturer who's supposed to be joining us in a little bit. His name is Royal O'Brien. He is General Manager of Digital Media and Games at the Linux Foundation and O3DE, which is an open source gaming platform. He is heavily involved in open standards for Metaverse, and I've had some really great conversations with him about that. His background is that he is a serial entrepreneur. He's a former Amazon exec. He worked as game tech chief evangelist. He has decades of computer game experience, and he brings that into the metaverse world where they're trying to solve some of the same problems. There's his Twitter handle, there's his LinkedIn, and that gives me a nice lead in here. So I'm going to pause the recording, and there's Royal. That's awesome. Well, then I don't need to pause the recording. I can just keep going. So let me switch to putting him on the front page. Well, it'll be
Hey,
me. Hey, Royal, how
how's it?
are you?
How's it? Good. How you doing, huh?
I'm doing well, thanks. So
Good.
I don't know how many people are going to actually jump on the Zoom meeting. A lot of people
All
are
right.
very camera shy, so I'm also streaming this on Twitch. So a lot of people
Fun.
will be watching it on the Twitch stream. So
That just means I need to put my pretty hair on.
well, that's easy for you because of
Yeah,
course,
right.
it's 11 in the morning there, and versus everybody else here where believe me, it's tough getting people to attend an 8 a.m. lecture class at university.
I bet. I bet.
So there we go.
Let's see. I'll be in here somewhere. I'm going with this background for today.
Ah, perfect.
You like
Perfect.
that?
Yeah, what a nice office you've got set up there.
You like that, huh?
I
I
think
mean,
I think I like your house better, honestly, but
uh, I'm a little favored to it. Of course, backyard looks like somebody dropped a grenade in it, so that's a whole other topic.
oh, that's
I mean, I
because
gotta go with the.
you're in the middle of construction, right? As always.
Yes, I am.
All right.
So, or I could go with the classic LF background.
So I did do an intro before you showed up, so there's
Good.
going to be something in the recording, so you can introduce yourself, and it's your talk. So I'm really looking forward to this. I hope other people are as well.
Good, good. Let's see. And I guess, if people have questions, they can always ask them if they're around.
Yep.
But I put together kind of a small deck so I can set the stage for a lot of this to help people get a better understanding of what's going on because there's an entire thinking of the practicality of what we're talking about in this environment. And so I'm going to talk about the incredibly big headache that we're facing of what's coming up in the future and what they should be thinking about. To be quite honest. So I'm going to share my screen here. And let's see. And hope that I had everything put together correctly. Wouldn't it be wonderful? Okay. So at this point, you should be able to see my screen, correct?
Yes, we can see
Good,
it.
good. Okay, so let's talk about. I'm going to talk a lot about here kind of 3D immersive worlds, elements like that, because the funny thing about it is that we know there are lots of big data models, but games, especially ones today, are massive data model sets, and they require a lot of data to be present very quickly. They need to be seamlessly. They cannot eat up the file I/O bus. They cannot eat up. They can't be chewing ERPs like it's going out of style. They can't be chewing up your CPU, or else people start losing frame rate. Play gets stuttered, causes issues. So it's one of those critical elements where time is never your friend. And you never have enough bandwidth or CPU or disk IO for any of it. And the minute somebody has to turn their settings down, they're angry. So we're going to talk about 3D immersive experience here. And so what's an experience? It's something that, where we load a lot of 3D data. We kind of put you into an environment where it's kind of like reality. It switches from what you see every day for your everyday surroundings into kind of a virtual environment, whether this be a VR environment, upcoming things people want to see in the metaverse, Call of Duty, whatever game. We deal with these things. And we're talking about in a larger scale, think of it kind of like what we talk about in context of metaverse. like a centralized hub where people will come to, and where you might see it happen, augmented reality, virtual reality. These have different parameters on how they play. Some of them don't need as much information. Some need a lot of information to be able to get this done. And the quality of it is going to depend on the device that you use as well. Mobile phones, tablets, handhelds, all of that's going to come into play, including LED screens. And hey, holodecks, right? Come on, we're all going to have one of those. So, and there's a lot of elements in how we'll be doing this. Like, am I looking at it from a first person view, third person? Am I kind of top down, isometric? That will dictate the amount of data that I'm going to need and the reality of it. So there's a certain kind of consistency that we have to create. And so we have to look at this from the perspective that there's a lot of data that's coming in. We have 3D meshes, we have textures, we have runtime formats, lighting, animation, shaders, scenes, all of these constructs. You kind of take it for granted when you look at like an HTML page. You've got your HTML markup, all the images and pieces that go along with it that make it interactive. People don't realize that, there's about 20 threads being fired off when you pull a page, it's pulling all this JavaScript to make it interactive. So today's experience is not like yesterday's experience of what it is. And today's experience of data needs of what we're doing in games and what we're doing in simulation will be very different from tomorrow's needs as well. So I'm going to set the stage of this here. If you look, there's an example of a 3D jacket. This is a model. Now, take note of it. There are different types of textures. There's a leather patch. There's kind of a tweed area. We've got the upper cotton area. So they're very different looking textures that are done to make it look realistic. And so when we're talking about these 3D environments, keep in mind that we're looking at what 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's probably about 15 different actual textures that are fitting on this 3D model for it to look nice. And this means that you're going to face that when we look at doing in clothing, avatars, environmental, landscape, architecture, objects, cars, vehicles, rocks. No matter what it is, they will all have a certain amount of textures that are involved, and you're going to have to figure out how to get all of this data. So here's an example of, when I talk about how that last image looked quite realistic. Here's an example of, kind of a grassy, mossy rock. And, you'll notice it's kind of a little darker on the right, a little lighter on the left. And it's because of the different textures that are used. So if you want to understand the magnitude of data that you're going to deal with here, we have multiple channels to achieve that look. And that one there, just the example has a base color, which is a texture, which could be a 4K, 1K, 2K texture. And keep in mind, they have red, green, and blue channels, and a lot of times they'll have an alpha channel as well. So 32 bits per pixel times 4096 times 4096 is a 4K image. So, but then I have to multiply it also by the number of channels. So albedo, ambient occlusion, how's it going to cast some of the shadows that you see over that? Displacement, how does we make it look like the height of it? The metallic surface look, the normal, the roughness, how does the surface actually look like it? This is what creates all the bumps and artifacts and elements and extrusions into it. And so when we look at this, here's an example to give you an understanding of how we mix these up to create realistic. You'll see the normal is very shiny, whereas I can define kind of the surface of that texture there. I can define whether it's how rough it is. Does it reflect light back? Does it look like metal? If you'll notice height, the difference in height it's how much it extrudes the object out. You notice we have rocks, and this rocky surface is no longer a circle. It now has a lot of bumps because we've extracted that information out. And then opacity, how much of it's transparent that should carry through and how much is not. And then, of course, ambient occlusion, saying how do I cast shadows when I throw light surfaces against it. So the whole point of this is when we start building these things and you're trying to create a real 3D environment, there's a lot of data. And you're going to want to use different LODs and mipmap levels to get this done. These are going to delegate how much of the information I need to send. So we have different lighting, we have shaders, we have different levels. Now let's get into the dirt of what we're talking about. We have a full texture resolution. It is going to look beautiful when it's right up in your face. But when you move further away, as an example, if you're on the stream, take a look at your keyboard. You can take a look at the texture of what's there. If you have a keyboard or something located across the room, you can't see that level of detail. which means I don't actually need to transmit that either. And so an 8K texture is going to be about 269 megs or 85 megs of data. At 4K, it reduces down to 67. These are uncompressed and compressed. About 30 megs, 8 megs, 2 megs, 520K, 110, 30, 8, 2. So you see how they reduce greatly depending on how they go. Think of what I just talked about. Okay. I just explained an outfit that had about 15 different physical based textures that had 6 channels of textures, each at a different varying level of data. So do the math on that. If I tried to make that look photorealistic like a movie at 4K, that's 30 meg times 6 times 15 before I've actually produced that simple jacket. And did I mention that was just a jacket? I didn't mention the other 20 positions on the body that I can draw clothing for an avatar. So now multiply that number by 20. And oh, by the way, if you're having to be playing around in a multiplayer environment, multiply that by 100 to 200 people. All of a sudden, your data payload is no longer even feasible. And so that's the whole point why I framed all of this to you to explain that this is reality. And so there are a couple tricks that we like to do that help reduce some of that data. And so now this is where understanding what you can do in distributed file systems and how you can do access patterns across the internet or on disk to kind of reduce this unfeasible, because let's face it, you're not pulling in terabytes of data. If I take a look at the example I gave you at 4K, it's 30 times 6 times 15 times 20 times 100 people. Yeah, that's a lot of data. That's 5.5 terabytes just to load into a single instance. So you're probably not going to be pulling that one off. So we do a neat trick here, and we do things with MIP levels. And so remember the point I brought up earlier, which was take a look at the keyboards in front of you. You can see the texture. That texture would be like 4K. I can see the intricate detail. I need that 30 meg. But as I move farther away from you, I don't really need that high level of detail because I can't see it. So in this example, for that environment, if I have an avatar who is 30, 40 meters away, I don't need a full 4K, do I? I can actually pull this off where I can maybe reduce it to maybe 128s, 30K. So let's do a little math on that. So now we say 30K times 6 channels times 15 times 20 times 100 people, our amounts reduce quite a bit if you consider that. So you're talking about literally what, 5.5 megs. So the point is that these reductions of what we're able to do all of a sudden becomes feasible. So you choose which MIP map levels and which LODs you pick depending on the distance of what they are and what you use. And this is normally how we do it. This is what also gives us the ability to stream things, to be able to create this visual consistency. And if you think this is pipe dream, wait until you see people try to do this in scale on metaverse or in any kind of environment, because this is the hard reality of what it looks like. And this image here is a great representation. You can see that the closer it is, the higher resolution image I use, and the further away, the lower image resolution I use. I can literally chop this thing down 300 times if I tried to use full texture resolution. But it's a lot of I/O and a lot of access patterns that I'm doing, because I'm not just framing out 4K 16, 4K pages or 16 meg, read forward caching, because I don't have these massive objects, 30 kilobytes of data. Yeah, you can squeeze that into a few, but it's not going to be framed off. And if I'm pulling these, MIP 16s, which I realistically would, because why wouldn't I at that range, then it makes a lot of sense. Now, this also applies when I'm talking about 3D objects as well. So the super high resolution car, that looks amazing when you're close to it. Nobody really ships that super high resolution thing. They have different different LODs, which are level of detail. So when you see the race car game and you see all these cars driving around, the reality is that that 15K polygon image that I have there, that I can put that down the road for 1,000 cars, and it's going to have very little impact. Think about it. At 15K, I can realistically put 30 of those cars in the same space as what I can put in for one car at full resolution. So these are the tricks that we do, and we change these dynamically. Okay, so you will be loading and unloading these objects as I move around in space. If I go back to the image here, what is 1K right now, and I take 30 steps forward, my 512s become 1Ks, my 256s become 512s, my 1Ks are that I had before, I don't even need them. I need to unload them, get rid of them. So this landscape will be changing constantly as you're streaming things in and streaming things out. And that's why, because distance is your friend. LOD0, we look at this, it's a great looking picture on the left side of about, 60,000 polygons. And the closer, that I get to the camera, I want those higher polygons. But the further away, I mean, I can literally look like an 80s game of, vector-based play. And 60 polygons is perfectly fine because it's far, far away. So this kind of gives you an idea of what are the things that you'll be dealing with, especially with interactive experiences when we're talking about media, because they will literally load these things in and out. And in some cases, they'll load a whole bunch of them. They'll just flip them in and out of memory. You'll learn that a lot of them like to pin memory into space. And so they'll basically make a page file, pin the memory, and be able to do pointer swaps on the fly to be able to pull those in for the optimal solution. So just to give you kind of an idea of what some of the application of this is. So going back to that visual consistency, now if you take a look at this point, I have 3D objects that are changing textures and sizes, 3D objects that are changing the number of points or triangles that are being loaded. I have textures that are being changed for triangles. And if you think about it, my landscape, if you've heard of digital twin, in digital twin, I'm also doing things by tiles. I'm sure you've seen in Google Maps where you have a slow connection and you watch kind of draw the squares in. Great, those are tiles. We do the same thing in the 3D space where we will load a 3D tile, we will seam it up to another and have the textures, and we change our LODs and we change our MIPS depending on the distance of how far they are, because it makes it viable for you to actually get it done. So you look at some of the formats that we're going to have to deal with here. And we have these kind of FBX, OBJ, GLTF, and we have texture formats that we bring in, and then we have platform texture formats. So when you're thinking about how you're going to load these things, how are they going to work? I'm going to throw one more wrench into the pile here, because if you think that was all there was, you're wrong. Because guess what? Those input formats that I mentioned of those textures, yeah, they're also per device, per platform, which means that the textures you load on Android versus the textures you load on an iPad versus the textures you load on a PC, they're all different. PC tends to use BC6 to BC7. You'll find out Android and iOS. Android, I think you'll find ATSC is used on different mobile platforms, DDS for others. So now here's your problem. Come up with a file system model that can actually load objects off of the internet based off of a device held in your hand, and 100 object requesters, as well as a landscape and tiled environment that is changing dynamically per second into an engine that is loading and feeding these things all in real time. And that is a realistic statement, because what I'm going to have to do is I'm going to present to the to the cloud or to a cache model that I have an Android device and I need a character and I need an avatar that has all of these different object placements, which that's going to change as we move them along. And I need to be able to switch those in and out and find those references fast enough in real time without holding the thread of what is trying to load that object based upon the demand request, without creating a lot of popping. So think about that, the robustness of what you have to come up with, where I'm streaming off the internet asynchronously. I am putting things on the disk and causing disk IO, doing a lot of creates, a lot of writes, and then also doing a lot of read calls back off of that to be able to actually use and manipulate them. And in some cases, they may be compressed, where I have to decompress some of them. They may be in a specific format where I have to map them in. This is a lot of stuff going on that can terrorize a machine. And for God forbid, somebody actually has an SD card in their phone. You're going to find out what mind-numbing experience is about because it does not open things and does not do things very quickly. And it's realistic. The other part of this is that you have relationships. Take our esteemed fellow rocker here with the guitar in his hand. So if this is somebody's avatar, think about what's involved here. They have accessories. That means there's a jacket, there's pants, there's boots, there's jewelry, there's hairstyles, there's the axe in his hand. And these can be centralized and decentralized, people that live in the same space or people that are all over the place across different environments. But if you get it wrong, where does that shoe fit? It winds up getting stuffed on his head. So now we have to look at the relationship so that when I actually do a read call and I call for boots, I need to make sure that I know where to put that. What is the relationship? What are the textures and objects that went along with it? And is there anything else complementing it? So this compounds the problem even more of what you're looking at. And this is all part of interoperability. You'll see this when different brands are trying to build this. So think about your IO. You're going to have to load a 3D mesh of a generic avatar. You're going to have to load the textures that go along with it. But then you're going to have to layer all of these other objects, which means that you have all of these things that have to exist at one moment in time that has been requested because somebody entered the world. So that means that you have all these objects, all these meshes, all these textures, times the multiplied amount of what we've talked about. And by the way, don't expect that you're going to be going to the internet and asking, can I have boots? Can I have this texture, this texture independently? Because the latency alone, you will cripple. I'm lucky enough to have fiber at the house, and they just upgraded me to 5 gigabit bidirectional. So I'm feeling a little spoiled. But no matter what kind of bandwidth I have here, here's the thing. If I send out 40 requests and I do them in a synchronous model, guess what? I just reduced that bandwidth to probably under like 2 megabit. Because the amount of latency transaction at 10 milliseconds for me to do a request acknowledgement to a web server or to a CDN server that's local. And by the way, 10 is screaming fast. And to get that data back on the transmit, even doing it asynchronously, I still have an issue with the amount that I'm going to flow through at one time per request. So this is where you've got to look at the relationships and the objects of what you're doing and how you're pulling them in. So you may turn around and say, well, I know that I've been asking for LOD 5 and I've been asking for MIP 256 of the boots, and I am moving forward in space. So I know that I should be doing some forward requesting and caching locally so that when I go to swap that pin out to move from MIP 5 to MIP 4, from LOD 256 to LOD 512, that data is readily available in a cached model that actually fits on a framed fence so that it's viable. Because if I do a lot of misses on it, I'm going to cause a lot of IO disruption. And if I start doing that, that's when I start causing a lot of problems across the board. And you'll see a lot of kind of stuttering, skipping. And remember, everything else is trying to hit the bus at the same time. So you're not the exclusive player here, okay? I'm having to move tremendous amounts of data into the GPU and sound banks and user logic and physics. There's so many subsystems happening at the same time. So the way that you construct your asynchronous IO and how you do your loading patterns and how you do forward prediction of data in the model is going to have a major, major impact as to how you'll do it, as to what the effect will be on the final experience. And that's the most important part here, is that you're trying to create an experience that people don't get, they don't fall out of the flow. They don't break immersion. There's nothing worse. Could you imagine everything that I just talked about? Now let me put you into an ARM-based VR Oculus headset. Okay. Think about, you're looking inside of this headset, wishing that you have at least 72 frames a second so you don't start hurling. And all of a sudden, your new application starts flooding the bus on that lovely little Android subsystem. And you're writing all your great, user mode kernel drivers to be able to do all of this fun stuff. And it starts stuttering up. Okay. I can guarantee all of your customers will be buying way more motion sickness bands and Dramamine to play your application, you're probably not going to get a lot of 5 stars. And why? Because your disk IO subsystem has been killing everything in sight. So take that into consideration when you're looking at the application of what is the efficiency of what I need to do, how I'm pulling data in, how can I do forward prediction, how can I do things that give me a lot more pointer swaps, and I can do that predictability in a manner that may not be a multiple of, an exponential of 2, because I can tell you a lot of times it won't be an exponential of 2. As a matter of fact, it almost never is an exponential of 2. And so you're going to have to deal with how will you make those things work in a system without causing a ton of faults. So, that gives you an idea of some of the areas that you're going to have to take into consideration when we're doing some of these models. So, so the other part here is that we're going to have to look at this for animations. Imagine if you send the animation and the data is not correct, and you want this guy to actually rotate around in circles, and he winds up pulling this video instead, which is, of course, we picked the wrong axis. So the accuracy of your data is also very important of what you're pulling in, and you can't just predict everything. So this data is, you'll have in some cases procedural. You'll have some shared data tables, which, by the way, congratulations, we're loading more data against this, because all of these shared data models are how it's going to tween between running, walking, jumping, turn left, turn right. We don't produce all of those. We actually produce different targets that give us at least data tables to tell us how to speed up or move the different bones within a character that makes them look smooth. And so then we have morph targets, which allows us to deform the facial expressions. Again, this is way more data. Think about the amount, think of the bone systems and what I'm trying to do to move them around. And I didn't even talk about the fact that all we started at here was, how do I show 100 people running around inside of a landscape? I didn't talk about them actually moving their lips or faces or actually walking around. So this is even more data, that you're going to have to deal with, or how you're going to push some of that. So something else to consider, how all of this comes together to create a realistic experience, which is volumes and volumes of data to work with. But let's talk about, if you're not a big gamer and you want to talk about digital twin. Well, digital twin, again, we're talking about a tile-based system in a very large coordinate space. If you look at Microsoft Flight Simulator, that thing is massive of how big of a game it is. You don't load it all. It's literally streaming it into you as it goes along, streaming you tiles. And it's streaming you tiles based on the LOD of the distance. If I'm at 10,000 feet, I really don't need to know the texture of the blade of grass on the ground. It's green. It's probably got a couple dots, and that's if I'm lucky to see it. So being able to take into account when we talk about digital twin or any of these environments, it will be important, because how people react and how you'll be looking at your data loading patterns will matter, whether you're in a VR space or a 2D or a 3D space. And then, of course, you have augmented landscapes. These are going to be a lot easier to deal with, because, granted, we have some of the characters we're pulling around, but our environment that we're drawing is a lot simpler. We're not having to actually construct everything. That's a part of it, but you will see some of these environments of what will be coming into play. So think about, how will you take a look at the relationships? How will you be given the information so that you understand what to load, when to load? How will you, be able to communicate with your potential customers or your potential employer when they tell you that they want to be able to show this environment, and you're the one who has to raise your hand in the room and say, whoa, there's a bigger problem here at hand of the things that we need to have produced ahead of time to pull this off. Because if you don't, and you're the expert in the room, why didn't you raise your hand? Because you should have known this. And it comes along with experience, especially with these large, with some of these large scale environments and some of the demands. I can tell you that this is a make or break for almost any of these environments. Now, I've given you a very extreme case, okay? Would anybody actually be using 4K textures across the board on everything? Of course not. It's not possible. Um, will they be using lower LODs? Of course they will. Will they be using lower MIPS? Of course they will. But it depends on who's in the room and who's aware of it, because they're going to have these suggestions to go, we want the highest fidelity and the highest quality and the highest this. And you're going to go, reality check. Your disk IO subsystem only goes so fast and you only have so much bandwidth to work with. And 5G will not save your soul. So just something that you want to make sure that you're bringing into reality, because if we go back to the numbers that I brought up earlier in this presentation, these are reality. When I brought up these MIP map levels, guess what? That's a hard reality. And when you tell somebody, hey, yeah, we can produce that 10 by 10 kilometer landscape, but by the way, it's going to chew up 70 to 80 gigs worth of data. And somebody's going to go, whoa, what do you mean? And you're going to have the math. And you're going to have to explain to them that you will be streaming this data in, and that the critical subsystem that you'll be writing to get this accomplished is going to have to facilitate this. The reason I bring this up is that in my past history, I had to do this with software with no integration at all, doing it purely with a kernel driver, and that's it. I had to actually catch read IO threads, take a look at what offsets they were trying to load from 3D objects and texture, and then make deterministic reads and progressions off of the internet while they're playing this game live, and people popping characters in and out on the fly, and I'm pulling them off the internet and trying to fulfill all these IO requests and holding threads in kernel space with no direct interaction with the actual game itself interaction. So I'm looking at it purely from a read IO perspective, that I know this texture begins and ends at this point. This 3D object begins and ends at this point and has these relationships that if it's a shield and I know it has 4 textures, if I'm loading the shield, I better go get those textures. And I better have them ready because they're probably going to come up. And I have to change my mind a lot. I will basically go, nope, I was just kidding. And I'll do that 20 to 30 times a second and be going after something else in a priority. And then, of course, there's always somebody who, we're playing in a landscape that is, like a sandstorm. There's not much out there, and some dude with a unicorn and a Darth Vader suit comes flying into the world. Guess what? It doesn't matter whether I can predict it or not. I still have to load it. I still have to present it. And it still has to be shown because the game expects it to be there. And it expects it to be there in a timely manner. So keep in mind, the math and distance is your friend, especially on how you're doing it. And you'll be able to frame out at least how much of a memory allocation do you need to make? How much forward read are you going to make? How much do you want to page against it? As long as you have a basic understanding of that, you can make these decisions. They'll have a big impact because there's going to be thousands of objects flying by per second. And you're going to go thread happy with it. And you're going to have to, because there's no other way around it. There's no blocking in this. Okay. You don't get that luxury. And that's just the way it is. And you'll find out that in the games industry, we have to be really, we're really scrappy. You have to be, because everybody has some kind of unrealistic thing that they want us to do, and we just have to magically make it happen in a lot of different ways. So in some ways, I would say we are the David Copperfields of coding, because we just magically make things appear. So think about treating objects that are coming in like video bit streams. Think about this for a second. You fire up Netflix, right? And you watch it, or Hulu. In the beginning, you notice they always have that Netflix trailer, that boom that goes through, right? That allows you to do some forward reading at a higher bit rate. But if you don't have enough to sustain it, you will notice that it gets really, really blocky. And that's because they're sending it to you at a lower bit rate until your connection can sustain the higher bit rate. So you're really not getting 4K off the on the onset when you first started it. You're probably getting like 512 to or 1 megabit, and it's moving up, but it switches bit streams on the fly on the next keyframe. And so when you treat your LODs like bit streams, that means that you'll be able to also, as they're coming in, you want to switch bit streams so that they have the ability of changing the textures so they're more accurate as they get closer to you. And you're going to be doing this both threading on your connectivity to the internet to a cache or a CDN, or you'll also be doing it as you're threading it on the local file system with that. And in a lot of cases, when you go to place this data locally, it's advantageous to actually pack a lot of that stuff into a single file so that you're not doing a lot of creates. Because we already know that doing creates in a file system is very, very expensive. And so if you can open a container and bring the data in and put it inside of a container and pack those objects and give yourself relative offsets, you can reduce that total impact of that incredibly expensive call. And instead pin the space and be able to kind of, forward read off of those. And you can keep those handles open if you want. It's not a big deal because you know what the prediction is going to be and what you're going to do. Control of flow of creates and closes are really critical to this. So keep that in mind when you're doing your architecture. Treat them like bit streams, treat them like how you're actually doing them. And when you're bringing them to cache, kind of pack objects that can go along together. If you wonder why games like to take big files and make these 500 meg and 1 gig and 2 gig files, give you a hint, it's less expensive on the creates because I can open these handles. If I have, think about it, I have a 20 gig game. I pack it into 10 2 gig files. I can leave 10 file handles open and never have to deal with another expensive call and jump all over the offsets and actually pin off different locations and make it really stupid fast. So consider it that way. Define the relationships between the objects, making sure that you know that things that are related that you will probably have load patterns on. If you have the luxury of being able to do that, pack them together. Pack them in a model where you can cross-reference them because that is going to help your performance substantially of what you're trying to get done. Multi-threaded. Let's face it, if you're doing a lot of asynchronous and things are being pulled in on the fly, most likely your engine is, or at least you will pray that it is, because sometimes you'll find some engine writers will actually write them where they have blocking IO calls. And of course, you're pulling your hair out screaming why this is not the 80s or the 90s, but you want to make sure that you're handling the threading of it, because here's the coolest part about being involved in a file system. You get to look like a slow hard drive. Ta-da! It's such a great thing because you don't have to necessarily throw errors. You can say, yep, I got you. I'm working on it right now. And that can buy you the little bit of time that you need, because engine writers and others that are writing these systems know that not every file system works the same. Some people, well, they're not using floppy, but they are using, maybe some are, but they're using legacy spinners, they're using SSDs, NVMEs, things like that. So they know that they have to compensate when that happens. They also know that when they put a demand on the file system, that it will slow down the overall file system's capability. So keep that in mind because you're going to want to compensate for that. Use your threading capabilities, keep your handles on the fly, and you can do that. Make sure that you have the content that's available for the platform. Don't pull stuff that you don't need. It's unnecessary, causes a lot of headache. I've seen games literally overshoot by a gig, cause 2 minutes of wait load time between one space to another, and then they get rid of the overhead, and it's like 15 seconds. So be careful what you're loading. Overshooting is really not very nice. And if you hit the page, if they don't have enough memory, you hit the page file, good luck. So keep placeholders for things. If you don't have the data ready and it's critical and you think it will crash or it doesn't have enough time, keep a placeholder readily available so that you can present something to it and then be able to keep the handle open or be able to have a communication with a callback that says, hey, I want to be able to replace this for you if you'll allow me to. Define your level of physics and colliders and things going that, but you want to allow these experiences to make the right choices. You're there to create the flexibility for them to make the choices, but you're there to also keep them on the rails. And you're going to have to do this per platform, because when you write the code on Windows, it's going to act differently than when you write it on Linux or when you write it on Android or iOS. They act very differently on that. And I, to this day, I think still the slowest possible thing that of what's realistically usable that you'll have today is the SD card. That is one, even though you're doing the same file IO, SD will be the bane of your existence. And and the problem is that you can't control the customer because the person who's using this application did not tell you, and that's too bad because it's always your fault. And that's just how it works in our lives. But as long as you take that into account and you know how to compensate for it, there are a handful of strategies that you can do for this sheer onslaught of data. So keep in mind that, a lot of these create formats, you want to make sure they're in the final destination, the final format of how you're going to use this with data. Because if you try to use the originate and create ones, not only will they have to convert, which means you're chewing up tons of CPU, but you're loading bandwidth that's really not necessary. And so you'll turn that cell phone in their hands into a fiery brick in no time flat because it wasn't made to be used on that device. It needed to be converted, and you chewed up a bunch of bandwidth that wasn't needed when you could have pulled the final compressed format that was usable immediately. You want to use a lot of the open formats. You don't want to make sure you have deep dependencies because dependencies are a nightmare. You try to load one object and you get 20. That's not the bargain basement deal you were looking for. So keep in mind that you want to make sure that you're very concise in what you're loading. And being able to kind of extend some of the formats and using some of the embedded formats that serve your purpose, where you can thread them out, you can do an action against it. And then also kind of redefine some of the formats of how they'll be used when they're on network versus when they're at runtime. So in other words, what lives on the network may not necessarily be in the best format of what you can do in runtime. And so if you have a little thread space to be able to do those optimizations locally, do them. Because here's the thing, you're only going to load the data up to a certain point of what you need off the network. This is not like you're doing pixel streaming off the video source where it's the longest data payload you've ever done. As the data comes in, you can do the optimization so that the second time it runs into that read call, it's already there, it's present, it's fast. And what it does is, as time goes along, you systematically get so much faster at your application that the more they use it, the longer they use it, the better the experience. So using the right tools for the job. In this case, this is more kind of focused around 3D and things like that. But you will be dealing with hot loading of assets and mergeable updates. So what you thought you had in memory will definitely change. If you think about it from a metaverse perspective, and some people believe in it and some people don't. But here's what I do know about it. It will not be, hey, guess what? This metaverse experience is down. We are in a service model for the next 4 hours. This is not World of Warcraft. You don't get to take the server down just because you have some new content. Expect it to be hot loaded and expect it to be mergeable because it will happen and you'll be doing the Delta patching. So if you've ever seen that before, breaking news, scheduled maintenance will be on this time and it'll be down for these number of hours. Don't expect to see that because time is money. And imagine if your favorite website, I don't know, some of you love Facebook or Twitter or whatever, went down for 11 hours. People would be starting riots, or at least you'd see it on CNN. So the whole point of the matter is that when we look at 3D experiences and metaverse, that also cannot happen here. And so as a file writer, you're going to have a lot of mergeable and hot loading of objects that will come in. So just be aware that these things have to be done. That's pretty much everything. So hopefully I gave you a little bit to think about. If you have any questions, knock yourself out.
Well, thanks, Royal. That was actually very interesting and entertaining, and I liked all of the references to technologies older than almost everybody watching. So that was great as well. Um, this is a pretty shy group, but I'm monitoring Discord to see if anybody has any questions. If you're in the Zoom channel, feel free to you can type a question that won't show up on the recording. You can actually turn your microphone on. That will show up. It'll record your voice. Um,
And if you've ever used an 8-inch floppy, I'll be impressed. Yeah.
and I have not ever personally used it, but I have seen paper tape.
Yes, yes,
Punch
yes.
cards we used when I was a kid in grade school for art projects. But people actually use that. So let's see. We have laughs and thanks, and so good feedback. Thank you guys. I'm trying to think of, and I'm listening to this talking, going, oh, this is the conversation we were supposed to have months ago. Great, thanks very much for that. So, and some of the things that you said are great because they echo the comments I've made, which is that moving data across the network is basically the bane of distributed systems, because of course the emphasis in this course is on distributed systems, and they've been fighting with consensus algorithms. So
Mm.
I've been teaching them quorum replication and Paxos, and of course um, you can sit down and you can read Lamport's description of Paxos as I don't know if you've ever read his part-time Parliament paper, but you first read it and you go, what just hit me? Because he literally is talking about a mythical Greek island, which actually isn't mythical. It really is
Hmm.
a Greek island, but it's a mythical legislature on this real Greek island, and how they legislate when nobody's in the same room at the same time, and they still have to come up with a concerted agreement. And so, like you were talking about, putting things together. And one of the things that a number of people have had to do in the project that we just extended the deadline on was batching. So
Hmm.
instead of doing things one at a time over the network, where you end up dealing with that latency problem and whatnot, you send a block of requests across. So that's similar to the way that you're talking about packaging up the data and sending data in larger blocks. And of course, I know a lot about what you've done, so I understand the idea that in fact what you really do is you just send this empty specification of how big the big blob is, and then you pull the little blobs that you actually
Yeah.
need in there as necessary, because that's actually how I met Royal in the first place. Is that was what he was doing. And
The
um,
crazy game guy.
well, and it is kind of crazy, but it's interesting because in storage we build these abstractions where the storage layer really doesn't want to know anything about the structure of your data. And then you come along and you say, yeah, but you're giving something up here, and that is you're giving up efficiency. You're basically building something that if you just simply look at all data as being nothing but flat blocks with no structure, then you are not going to be able to do anything over the internet in a streaming fashion.
Yep,
So,
that's actually, so it's funny you bring that up because that is a critical point. Is that so? The example of pulling these blobs, being range requests using ATP range requests, that you can do from a cache. So if everybody remembers, there was a point that I brought up of saving larger files on the local disk subsystem, but you can do the same thing over the network where you can put these same 2 gig files up on a cache server, and then do a range request to get sparse points, and it brings it down as a giant blob. So, that is where I can do 50 to 60 requests in one single request and one single latent object that comes back with a large, and then I can sift all of these pieces out. But the funny thing about it is that when you look at that model of how you're doing that, now you have the opportunity to do something locally that wasn't in the same order of what had existed on network, but now operates a lot better locally. So, these patterns are critical, but here's the thing. You're given so much hinted information and data to work with on these distributed systems that why on God's green earth would you not want to feed it into an AI model to give you some forward predictability and at least feed you a hint? We do it in everything else. We do it in animation. We do it in textures. We do it in all these different objects. We do with that. So having just the raw data of an offset and a range can tell you a tremendous amount of information of what you're about to deal with in a distributed environment.
mhm.
It's definitely something you want.
Oh, and so for all intents and purposes, having the name of the container, the offset, and the range then becomes a form of a key.
Hmm.
So then you can reason about that. And the reason I mention that is because the students are primarily using a framework that was developed at the University of Washington for teaching these distributed consensus protocols, and it's all key value stores.
Right.
Basically, everything is a really super simple database. And um, I know I've mentioned this several times. I've actually been criticized for talking about file systems too much in the class, but of course, a file system is really nothing more than a naming layer on top of a key value store.
Hmm.
From an implementation perspective, and in essence, what you're saying is that, well, actually, that key and value that you stored in this database really has substructure to it. It's more keys and more values inside of it. And it is useful for people to understand that that number one, we layer things because of course, if it's worth doing once, it's worth doing several times at different layers in a stack. And number two, these models do recur repeatedly. We see them in real world cases like this.
Yep.
Oh, let's see, we've got a
Yeah.
we've got a
Modern.
question.
Yeah.
Awesome. So in modern video game VR experiences, do we store most of the data on the local disk? I'm wondering about all those MIP maps and LOD textures and if we are always streaming them. In modern Call of Duty, would we have the maps and character models entirely local and mostly be streaming in the interactions? Good question.
Yep, great question. So the answer is yes, they're actually all local. Ironically, on the source material, you'll have, say, the 4K image itself as the source. And when they go to produce the game, that is going to produce a 4K, 2K, 1K all the way down. The interesting thing is that it only produces about 30% extra data payload for those 10 different LODs. And so they'll take all of those and they'll pack those into the same files. And that's the reason why your Call of Duty is like 80 gigs, because all of the LODs and all of the MIPS are actually there. And they're literally streaming them in and out on the fly from these files, from these packed files, what they do. And the interesting thing about it is that, going back to what Tony just brought up, is that they hash almost all of them. Everything gets hashed for the speed of lookup. Like, they don't go looking for a file name. They know what the hash is to find the object to get right to it. And so the file system is really just the abstraction underneath of it. If theoretically you could fit the entire thing in memory, you would, and you would pin against that and use your offsets.
Um, so that makes me curious here. So that works great if what you're doing is limiting yourself to a single multiverse platform where you've been able to preload all of this content. But you were specifically talking about how you want to be able to pull things in from other multiverses in a dynamic fashion. So um,
That's right.
so that works great for Call of Duty, but how well is it going to work for um, I don't know, this environment where we're really trying to get interoperability between Meta's version of this and I don't know, Microsoft's version of Metaverse?
The difference between them is really depends on the application of it. To be honest, it depends on what the environment of the engine is as well. So there's a couple elements at play when we talk about this. So, if we look at each version of what the metaverse as defined, the only way you're going to achieve interoperability is where the objects can traverse from one to the other in a meaningful way. So, will the data be so different? Well, here's the thing. If you want somebody to be able to use content from one to another, they're going to have a same common interoperable format. And so you'll find out a lot of the patterns of what you'll be learning on how to work with these indexed type models will apply the same, because if they're all independent and none of them actually, if I can't see a hat in one metaverse look like a hat in another metaverse, then simply put, you're not in a metaverse, you're just in a VR game.
Which isn't as useful, is it?
Correct.
Awesome, great answer. And I have a question off of Discord, so I will read it here. Is the rendering of different 1024, 512, 256 textures also based on the foundational idea, like in games, where it dynamically renders what you pan around to see in your current FOV, field of view? Uh,
Yes.
okay. And
Yes. Oh, sorry, that
oh
wasn't
yeah,
the question.
well, and then they have a long block afterwards. So yeah, so we'll start with a question, and then I'll read whatever it is they said afterwards. Okay.
So the actual LEDs, if you look in that other image that I had shared, that is kind of a real-time draw of what's going on in the engine. That's actually saying that I know all of these textures and objects need to be at this range and this distance. And so it's actually telling it which versions or which MIPS or LEDs to load. And this is all done in real time. It's part of a streaming subsystem.
Interesting. Cool. So then they continued on. I think I've definitely heard it in the past that at any given time, like in an open world RPG or a first person game, that most of the world really isn't there, even though the player feels immersed into thinking it is. But it's just dynamically loads in just the pieces of the world and its components as the player moves the camera so that they shift into the area deemed visible to the player.
So a lot of the world, you're right. A lot of the world is not necessarily loaded directly in GPU, but there is a pretty good amount of it. We do culling and occlusion to try to compensate for that. Like, I don't need to draw backface objects that I don't actually see. And so we do the culling and occlusion of that. And that's all done at runtime. There's a handful of like third parties, and it's kind of been baked into engines forever and a day now. So portions of it are, portions of it are not. And it depends on how robust the rendering engine is to be able to do occlusion and culling.
Cool, cool. I just checked the Twitch chat, which I never check, but I get to do that because I'm not the one talking in the middle of the classroom. And somebody just gave feedback. They said, "This is great, well done." And that was a DK Knight Gamer, which I think is great. So you know that um, apparently lots of people in academia don't use Twitch for streaming their classes, but I have been streaming the class on Twitch since day one, and um, and it's clear there's a gamer contingent here. Gosh, shocking that people going to university right now would actually do some gaming. So I have another question off of Discord, and this says, do we have to take into account the different kinds of memory on the device itself to get best possible load times? So for example, in the new Apple chips, we have this integrated memory pool, whereas most conventional machines have separate graphics and CPU memory.
So at the end of the day, it's going to be, you're going to, all right, so there are different calls. There's actually some newer calls that can actually do what's I think it's called direct read that Microsoft has. It allows you to actually pull things directly in, but you still have to load the object from memory space into GPU space. Even though some of them use shared space, you still, to be able to GPU to render it, it needs to be into a GPU space to be able to do that. So the blurring of the lines per se of cross memory space is a question of, am I using GDDR5, GDDR6, or am I using LPDDR4 off of what the local system is doing? So reality is you're probably not loading directly from the disk subsystem straight into GPU space because it's kind of a more modern thing. So you're still going to have to kind of bridge over those two because I'm not positive of this, but I don't think Apple has it written where the direct subsystems are loading straight into GPU space, because that'd be a whole new call to be able to do that, because obviously that is an isolated case. That's not a normal disk subsystem load of an object.
It isn't yet, but it could increasingly become one, especially as
Yes.
you continue to push uh, the rendering requirements of being able to support these metaverse uh, applications on mobile devices, for instance.
Right. It's the key here is that it would be its own call, though. My point is that the
Right.
call would actually be a load GPU call and not a load object call. So that would feed to that.
Interesting, because as you were talking about that, I was thinking of RDMA models where
Mhm.
you really can't tell that the memory isn't even on the local computer. But
Right.
at that point, we're moving away from even a file systems model for storage and moving towards everything is memory mapped for
Right.
all intents and purposes. Uh, and I know that those models are now used in data centers. And based on
Mhm.
the history of our field, any technology that gets widely adopted in data centers tends to creep down into consumer devices because it allows us to build new and interesting competitive products.
Well, look at the model. So, give an example of that is if you look in a large scale simulation model,
Mhm.
you'll have you'll have a server that may have 256 CPUs. And the reality is that you will have, or 128 CPUs, you'll take that and you'll feed that thing with, I don't know, terabyte of memory.
At least.
And what you'll do, yeah, or a couple tera, I don't know, whatever. But the point is, you'll take that memory and you'll run one of the services, one of the CPUs, and that'll be kind of your manager core. And your manager core will pin the entire thing. It will page pin that entire memory. And
Hmm.
what it'll do is it'll hand that pointer over to 64 or 128 instances of compute processing that is doing simulation for each one of the sharded nodes. The advantage is that when I need to move from one node to another in a meaningful way, it is nothing more than a pointer memory shift
Right.
is all it is. And I can move you from container to container inside of an enterprise environment by managing the underlying memory instead of giving all of my instances a chunk of memory and having it try to transfer over. You literally remove the copy operation and you also maintain the atomic nature of transfer without incurring the penalty of doing holding a lock,
Hmm.
holding a CPU lock.
Um, Yeah, no, that makes me think because you were talking about the size of the memories. That made me think of the work that I did with Optane before Intel basically decided not to continue down that road. I think it's just a matter of time before we see other persistent memory technologies emerge because there are compelling use cases here, and that's where uh, some of what you're talking about, where literally I had machines with 6 terabytes of persistent memory on them, and you really have to change the way you reason about things. So, like you're talking about these memory mappings, and one of the things that I observed because I published a paper about it was um, just the cost of fragmenting this stuff up into 4K and 2 meg pages on an Intel platform, the overhead of taking the TLB misses and
Mhm.
walking page tables for things that were never going to move was insanely high. So it does require a lot of rethink as we keep doing that sort of thing. And that I thought of that because of the RDMA discussion as well.
Yep.
So and the other thing that you mentioned that reminded me is that your workload is primarily a read mostly workload,
Yeah, actually, until you're actually doing on-the-fly Delta updates, I would still say that 90% plus is read,
right?
because you place data and you're just doing constant reads against it. That data does not change very often.
Yeah.
Now, that's today. Tomorrow, which I've been thinking about the models behind that, because now when you're looking at AI, the people who think about metaverse and forward 3D experiences, AI will be able to reshape entire environments, which means now data will be shuffling and shifting. And now you'll have read calls plus Delta IO updates combining at the same time in memory calls to alter environments on the fly. So consider a baseline plus patch, and that patch changes continuously, and you're merging in memory space while in operation. It's such a beautiful nightmare.
I was thinking that consistency in that model is going to be really hard to maintain
Oh,
because you could end up literally like loading different versions of things that are mutating. So this is
yeah,
great
it's
because this is exactly the environment that we've been really focusing on and studying over the course of the term is, how do you come up with somebody said, oh no, Project 4 flashbacks. Exactly. It's like and
but these
so
are real.
they are real, and I think that's what I really like about this conversation is because the students are sitting there thinking you are a sadistic person to make us use this unrealistic model of things going on in parallel and messages getting reordered and whatnot. It's like, no,
No,
actually, this is the
that's going to
real
happen.
world.
Yeah, this is what we have to deal with, especially in mass scale. It's different when you think of it in a small scale when you're like, 100, 200 people. I'm talking about 100,000 to 100 million. Okay, that's I can sneeze on 100. That's easy.
Right, right. But so like the read-only workload thing is important for them to understand though, because you build different systems when you have a very heavy read workload versus when you have more balanced read-write workloads or very heavy write workloads. Because we've
That's
talked
right.
about, I've spent a little bit of time talking about more write heavy workload solutions in distributed systems, but most of the emphasis is in caching, like you were talking about,
Yeah.
where you don't cache objects that change all that
Correct.
often. I think the lecture last week was about Facebook's use of memcached and their own homebrewed system Tau, which
Hmm.
are web caches, and they're just glorified key value stores of
Yeah.
things that don't change very often, but they actually do have a consistency protocol on top of them. The
Hmm.
problem with those consistency protocols is that unless you design them for purpose, if you literally have people who are sitting there changing things all of the time, and you're assuming they're not going to be changing things all the time, it just isn't going to work right.
Yeah.
So that's cool. Um, do we have any other questions? Let's see. I'll check Discord one more time. Oh, there's something else. Let's see. There is a question mark at the end of this, so I will ask. Since something like Metaverse cannot have downtime and new updates have to be merged while users are still in the space, i.e., the way you say hot loaded, how would you handle cases where someone is going around in an area that is actively being updated to include new visible objects and such? It might be a bit surprising to see things all of a sudden popping into view. Are they not real time in that way, maybe becoming visible when they reload the area, like leaving and coming back?
That's right. That is one of the approaches that you can do. You can also take a look at when they're making a delta change. Does it have a seamed edge object? Seamed edge objects are pretty good. If the LOD is far enough away, those are things you can also do. So, the popping effect really only happens if it's within a certain range of what you can see. Once it gets far away, then that popping kind of goes away because maybe you're only changing a handful of pixels and you can't really tell, and they're moving around changing already because of the distance. So it is what is close range, what is at distance, and what you can load as you're moving through the space. So if I make you walk from one end of the room to the other, the far end of the room that is away from you right now, I can change those objects because I know the LED is far enough away where it's not going to be as much of a drastic effect. But as I move through the space, whatever was behind me, as I move away from the LED distance, moving to the other side of the room, I can hot load those so that when I turn around, these things are starting to change. And that really depends on, you don't want the technology to dictate that. You want to make sure that the actual project operator and the content creator have the controls as to how they want to actually do that.
Well, that just makes the problem harder because, of course, nobody's going to choose the same thing. They're going to be choosing different models for this stuff. So now you have to
Well,
support
that's
everything, right?
yeah. I mean, you can dictate it, but the reality is that now you're basically prescribing what it should look like. And when somebody wants, here's the thing: people who are in an immersive environment, they will tolerate a certain level of, kind of inconsistency because I know it's still trying to get there. But if you make it so drastic, they're gonna be like, hey, this site is janky. Okay, this is not gonna happen. And so they're gonna leave. So the reality is that your ability to make money is also going to be tied to the experience. So your controls will delegate that. So yes, you will have to support kind of everything, and you'll have these rogue people that are like, yeah, I mean, just I want to pop it when they're at LOD zero, and which of course that would be a nightmare, but why not? So there are some elements here that you can change. It depends on how you want to do the controls.
Awesome. So that person had one follow-up comment. And they said, so instead of scaring them by popping in front of them, we might scare them by, hey, that wasn't there before, like some horror game. Ha ha ha.
Yeah, that's pretty much it. That's I have one of the I run I'm part of the Linux Foundation, and I run a foundation called the Open Metaverse Foundation and the Open 3D Foundation. And one of the slides that I do in those presentations is that the metaverse can do way more damage than the internet can do, because you can go on a web page and you can turn your head. If you turn your head in the metaverse, something else is going to be there. So yes, you're right. And you
Uh,
cannot unsee it.
Very good point. Very good point. Well, you know,
You
uh,
you think Scary Mary is the thing? Wait until people start doing that on the metaverse.
awesome, awesome. So we've kept you for over an hour now, so I think people have asked some good questions, and I've certainly enjoyed the discussion. So do you have any final parting advice for these? Basically, pretty much everybody in this class is graduating this term. So they'll be off, moving into various roles. Some of them might even be working in actual game development or metaverse development. So
So my suggestion is that, a lot of these different places that you're looking at and different theories, get involved in open source. It's the greatest playground, that you can actually put your hands on code. You can experiment. You can, kind of do some of your wildest dreams. You can find a handful of people that are, kindred souls. And most importantly, as you're building these things, you have a public CV of work and code and things that you've been doing that shows you to be kind of a thought leader, a project leader, an innovative person. It's where you don't have to prove it on your resume. It's a part of who you are and what you do, and the whole world gets to see it. So, if you're playing along with metaverse stuff, I would say, be happy to have you talk along with the fun stuff that we're doing in Open Metaverse, which is about building standards and building interoperable software libraries that are reusable. But I would definitely say, if you haven't looked into open source, you should, because it has a great number of benefits for short-term and long-term career. And when architecting, be crazy, be nuts, because the future already is. You just haven't figured it out yet.
great. Well, I know I appreciate that advice. So uh, if people want to give thanks, I mean, the downside to doing these kinds of meetings, of course, is you don't actually get people standing up and applauding you. But
Yeah.
I certainly appreciate it, and I can see that there's at least two comments. Well, there's one on Twitch and one here on Zoom, both of saying thanks very much. So Thanks everybody for coming. Thank you, Royal, very much for taking time out of your day and giving a great talk.
Thank you. I appreciate it. If anybody wants to reach out to me, my email and LinkedIn's up there. So, and if you get into the games industry, definitely reach out. I've been a part of that industry for over 25 years, so I might know a couple people.
Most of these
And
people
thank
aren't
you.
even 25 years old. Just got to make you
Thank you.
feel old, Royal. Hey, no problem.
Thanks, buddy. I appreciate it. Thank you so much for having me. I really appreciate it. This was a lot of fun for me as well.
Thanks. Awesome.
All
Thanks,
right.
everybody.